Lots of definitions. What is temperature? What is heat? What is the third type of energy we're looking at? We already looked at, you just had a quiz on potential, kinetic. This is the third one. What is temperature? Can you define it? You know how to use it. You know what scale we use in Canada. What's it called? Celsius. What do they use in America? Fahrenheit, named after, wasn't he an American?
No.
Correct. How do you know that? No. Yeah, Fahrenheit, he was a German. Anyway, kinetic molecular theory, KMT theory. Remember this from grade 8 science? No, of course not. But all we need to remember is matter is made of tiny particles and they're constantly moving, right? The faster they move, then what? More energy they have. Okay, a little more detail. These things can move in straight lines, these molecules. This thing looks like, I don't know, hydrogen or oxygen or something else that's diatomic. I don't know. Okay, helium. This is translation. Hey, it sounds like math today, doesn't it? Let's translate this molecule from here to here. Okay, anyway, it's moving in a straight line. It could be rotating. Technically, that's still motion. Does it still have some velocity? That's a good argument. It could be vibrating. All of these are what we would call kinetic motion, but in this case, we're concerned about energy, right? So these are all moving energies, so that's what we call kinetic energy. We also have potential energy of this thing, because this thing could have a charge, and maybe it came close to some other molecule with another charge, and they could be attracted, or maybe they repel, right? So there's potential energy. So all the kinetic and all the potential, that's a definition for thermal energy. That's something may or may not have. Okay? So, this is probably, 10% of your test. And like I said, it's the memorization type 10%. Okay? So, translational, just said it. Rotational, just had it. Vibrational, there it is. Potential, just talked about it. This is the total energy, what we call thermal energy. Now, what's heat? You could be like, here's a conversation that goes on the weekend with my wife and I in the car. She turns to me and says, "How hot is it?" Says it just like that, too. And I say, pull down the window, put my finger out, and go, "Oh, it's pretty hot." She looks at me like this. And I look at her like this. And then she goes, "Oh, okay, I'm a science teacher, right? Ask me a question I can answer." "All right, what's the temperature?" And I look at my car and I go, "Oh, it's 18 degrees. Why do you have to do that every time?" Okay, just wait till you're married. It's great. So, like I said, I'm a science teacher, right? How hot is it? Is that a relative statement? What does that mean? What is heat? Blah, blah, blah. Here it is, the amount of energy transferred. So heat, a measure of something's heatness. Does that sound right? Not really. Heat is just a transfer of thermal energy. So if there's no transfer involved, technically there's no heat. How hot is something? Well, you're asking me what the temperature is. Okay? All right, so temperature. Here's a scale we use in this country. Actually, it doesn't say it here, but Fahrenheit, there's this German guy, and what he did to come up with a scale is, how cold can I get this mixture of fluid before it freezes? Does that kind of sound like Celsius? But his fluid was actually a brine mixture. It was salt water. And he said, it's about this temperature. I'm going to take this salt water and call it 0 degree Fahrenheit. And then I'm going to go up to something that's like a body temperature normally, and I'll call that 100 Fahrenheit. Okay? Now, our scale, we didn't take brine, we just took pure water. When does it freeze? Yeah, pretty close. And then we took it as where does it boil? And then equal increments in between. Okay? Same thing with Fahrenheit, only their 100 is equal to 212, right? And our 0 is their 32. So what is this? What is the... You can experiment with different concentrations of salt in water, but if you try to put it on your road to make sure you don't skid your car under minus 18 Celsius, it has no effect. It'll still freeze. So that's the lowest you can possibly get salt water before it freezes, provided it's the right concentration of salt. So anyway, that's what he did. So this is all temperature, right? What is temperature? What does that say? Temperature is average translational kinetic energy. I first said at the beginning, we put heat into a system, and you know from grade 8 science or some other places that these molecules move faster and faster and faster. The faster they move, that's a measure of its temperature. And you know when temperature is too high, it hurts. And maybe it hurts when it's too low, too. These molecules slow down and slow down and slow down. So, here's a system. Let's give it some molecules. So there's, I don't know, nitrogen. Doesn't look diatomic though, but let's just assume it's nitrogen, okay? There's a bunch of nitrogen stuff in there. Now, if I add heat, what happens to these molecules? Yeah, they go faster and faster and faster, right? So that's a measure of its temperature. It's translational kinetic energy. Doesn't say rotational, doesn't say vibrational, just translational. These things are moving in straight lines a lot faster. What happens if I take heat out of the system? Notice the thermometer on the top. Coming down, coming down. How much can I remove from this system? Where's this heat going, by the way? It's transferring from these molecules to this ice pack here, right? Okay? How low can I get it? What if these things come to an absolute standstill and there's no motion at all? Yeah, do we have a word for that? And guys have done chemistry, you've done this. And what kind of a scale did this person come up with? Yeah, so those are almost dead stopped. In theory, I mean, how much more heat can I remove? That's it. Right? If they're not moving anymore, we call that 0 Kelvin. Okay? That's named after, well, Mr. Kelvin. He was a British lord. Okay, that's not that long ago, right? Like 1900. But anyway, this is his scale. So 0, he took, and that is what we would call, for Celsius, let's actually do a little table. So here's Kelvin, and here's degrees Celsius. So absolute 0, that's as theoretically as cold as something could get. That's minus 273. Now, luckily, it's a linear system. Okay, so Kelvin, if this is 0, then what is that Kelvin? Add 273, right? And if something boils, we know that's 100 degrees Celsius. So how much Kelvin is that? Add 100. Okay? So you're going to get a couple questions looking at that, and they'll give you Celsius, and they'll say convert it to Kelvin, and how do you get from 0 to 273? That's all you do. And then now it's in Kelvin, right? Okay, so not too much to it. Fahrenheit we're not doing, but basically add 32 and double it, or half it and minus 32 or something like that, okay? It's 5/9, but essentially it's almost 5/10, which is double. Okay, and lastly, the transfer of heat. How do you increase or decrease temperatures? There's 3 ways. Conduction, have you heard this word before? If you touch something hot, it hurts, especially if it's like a good conductor like metal. Conduction means, it's just think of electricity. We have free electrons and that bounces off that one and so on and so on. And however many free electrons we have, metal has lots of them, then the temperature from this end to that end will be very, very quick. Okay? If you're grabbing on this end, you hope it's not metal. You hope it's something that's a better insulator, like glass or asbestos, but then don't breathe it. Okay? So, same thing. Conduction, usually metals are good conductors, but that means it's a transfer. It's a physical contact, molecule to molecule. That's how the heat moves. How would you heat your house with conduction? You would take maybe a big hot rock from a fire outside and stick it in your living room, and then everyone would gather around it and touch it really quickly. And then you get warmer, mostly from the movement of touching it back and forth. Okay? So not a very good way to heat your house. Convection. That's a different way to transfer heat. This is when we heat a fluid, like a gas or a liquid, and then it moves from one place to another. Is this how we normally heat our houses? Yeah, we have a forced air furnace, powers on natural gas, and it heats the air and blows it around your house. And then that nice warm cloud of air comes and circles around you, and you go, ah, nice, right? So this is a movement of actually something that already has that thermal energy moving to you. So it's different than conduction, right? There isn't actually something here that touches you. So that's great. Now we know the main source of our heat is from the sun. So is there a big long metal rod connecting the sun to earth? Is that how we heat it? Is it conduction? No. Is it convection? Does a big cloud of starburst stuff, little fruity gums, come and travel towards Earth and surround us and give us that warmth? Is it some other cloud of something coming here? Or is it just space in between us? No particles of anything? Okay, all right. And that's how we get northern lights, right? From those flares. Send particles this way. Takes, I don't know how long, but then it hits our atmosphere and they glow, nice pretty colors and stuff. And actually last year has been a year that we've had more than historically, maybe forever. I don't know, from what I read. No, there must be another way to get heat, right? That's what brings us to this. Radiation. You go in stores, and sometimes to get in the entrance, because they have two big double doors in the winter, like you walk into Winners, they don't want all that cold air blowing in, so they always have heaters right above it. And if you ever notice in your house, that's where they have all the registers, under the cold windows, right? So sometimes it's actually hot air they're blowing at you, but other times it's infrared, right? They put in a gas and it just burns, and you just feel the warmth. There isn't actually anything touching you. It's not blowing towards you, but you still feel heat. That's radiation. Infrared. You can't see it. It's not part of the spectrum we can see, but we can still feel it. That's how we get warmth from the sun. Okay? It's God knows how many hundreds of thousands, millions of miles away, you still feel the heat. Radiation. All right? So read this. It's good stuff, but here's your questions. Tomorrow we have a lab, so no questions tomorrow. And like I say, there's not really very many numbers in these. This is like biology stuff, right? How do I? That's probably 159. I just can't read my own writing. Yep. Okay. So still got 20 minutes to get those done.